Hi, this is Jenny Lyon, and we're going to start population.
Right, so the next PowerPoint slides are for the population objectives. These are due tomorrow, along with the living world objectives. So number one says that you need to know the world population and U.S. population. It's very important that you have an idea of these numbers. You may be asked them just in a multiple choice question, or you could be asked to use them in a math problem. So on the left-hand part of the screen, you see the top 20 largest countries by population. You need to know at least your top 5: China, India, United States, and Indonesia, and Brazil number 5. You should also note that India, we expect to pass China in the near future. You can see United States, we're sitting at currently 322 million people. But if you're doing a math problem, you may want to round that to either 300 or 320 to make that number easier to work with. Our current world population, over 7 billion people, 7.2 billion. Also a good idea to round to 7 billion if you need to use this in a math question. Really easy to put it into scientific notation. All right, so number 2, know the 4 stages of the demographic transition model and what happens to the population, death rate, birth rate in each stage. The demographic transition is a process that has occurred during the past century or so. And as you look through this model, you'll see that it leads to stabilization of population in more highly developed countries, so closer to our stage 4, which is a post-industrial stage. You need to know the name of the 4 stages. So stage 1 is the pre-industrial stage. Stage 2 is the transitional stage. Stage 3, industrial, and stage 4, post-industrial. You also need to understand what happens to the birth rate, the death rate, and the population in each stage. So for stage 1, the pre-industrial stage, you can see that the birth and the death rates are both high. And because they're lingering around each other, we're going to have a stable population, or ZPG, zero population growth. The reason why the birth and death rate are high, there's poor medical care, or it's non-existent, limited food supply, and the birth rate remains high to compensate for the mortality rates. Stage 2 is the transitional stage. You should note that in this stage we have a very fast increase in population. So it's the stage where we have the biggest population growth. Birth rate remains high, but the death rate falls. The death rate's going to fall because we have advances in medical care, improved sanitation, and higher levels of education. The birth rate continues to stay high, so the population is going to grow. Sub-Saharan Africa would have some countries that are examples of this stage, excluding South Africa. So you can think of Nigeria, Niger, Ethiopia. These countries are currently in the second stage of the demographic transition model. Stage 3 is the industrial stage. You can see at the beginning of this stage 3, we see the population start to slow. We're seeing finally that the birth rate is reducing and coming close to the death rate. We're seeing families desire less children. We're seeing people move to urbanized areas. Women are now being educated, so they're looking for jobs, and so they're going to have less kids. Some examples of countries in stage 3: India, Mexico, South Africa. And then lastly, stage 4, the post-industrial stage. You can see the population will start to even out as the birth rates meet the death rates. We also see ZPG, or zero population growth, in this stage. And you can tell at the end of the stage that the birth rates actually fall below the death rate, causing the population to decline. So looking through this, we have at the beginning of stage 4, we would have countries like the United States, Canada, countries in Europe, and then at the end of stage 4, or if there were a stage 5, we would see countries that have declining populations. Germany, Italy, Japan, those would all be examples. Okay, for number 3, it says that you should be able to calculate the growth rate, including immigration and emigration. So you can see the equation here, and on the second page or the back page of your objectives, you'll have to use this equation to figure out some of the answers to the math problems. But you can see your growth rate is lowercase r. We have our birth rate minus our death rate plus the immigration minus the emigration. So immigration, the number of people coming into an area or into a country or into a city, and the emigration, the number of people that are leaving. So the births, the deaths, immigration, and emigration. All right, for number 4, you should be able to calculate doubling time. The rule of 70. The rule of 70 roughly explains time and how it's related to exponential growth with a constant rate. So you can see doubling time is the amount of time it would take for a population to double. Really easy equation. You need to memorize this. They're not going to give you any equations on the exam. But your doubling time is going to equal the number 70, always the number 70, over the growth rate as a percent. So for example, you would possibly be asked to, so 70 over 1.2, if you divide that out, you'll round to the nearest whole number. And you come out with a decimal, so you're going to round to 59 years. All right, number 5, describe the main reason why our population has grown exponentially. So the major reasons, due to medical advancements, people are living longer, and also the Industrial Revolution. Total fertility rate, also known as the TFR. The TFR is the average number of children that would be born to a woman over her lifetime, or the average number of children a woman will give birth to in her childbearing years. Here you can see some TFRs around the world. We should note that the United States has a TFR of about 1.9, so less than 2. Again, this is an average. Japan, 1.4, so they have a low TFR. And a country like Nigeria, it's about 6. So 6 children per woman. So in general, less developed countries are going to have higher TFRs. These countries, they're going to need more children. The women in the families are going to need more children. There's high infant mortality rates. They're going to need help on their farm. They're going to want a family to help take care of them when they're elderly. Here you can see world historical and predicted total fertility rates, 1950 to 2050. So we're looking that the TFRs are coming down. So looking at this, you can see our world total fertility rate, approximately 2.5, 2.49 here. Okay, replacement fertility rates, also known as the RLF, or replacement level fertility. And this is the number of children a couple must have to replace themselves. Most developed countries were looking at about 2.1. And developing countries, we can see between 2.5 and 3.3 due to infant mortality. Age structure diagrams. This is showing you some generalized age structure diagrams. They're an indicator of future population trends. And you have three main shapes here. You have an expanding population, you have a stable population, and then you can see the declining population here. Your expanding population is going to look very much like a pyramid. So you're going to have more people in the population under the age of 15 in their pre-reproductive years. And we're going to assume that they are going to grow up and reproduce in the future, so their population is going to continue to grow. Stable population, you can see we're going to be pretty even between our pre-reproductive years and our reproductive years. So it's going to be pretty even on both sides in these two categories. And then our declining population, we have fewer people in the pre-reproductive period or category than the others, or than the reproductive. So we have fewer young people, and fewer young people mean that there's less people that are going to have offspring and children, and so the population here would be declining. Here are some examples from our notes. So you can see Nigeria, this would be rapid population growth in the future. Again, we're looking for under the age of 15. That's considered the pre-reproductive years here. Sometimes on this x-axis you'll see either the number of people in millions, or you'll see it as a percent of the population. But make sure you note that the one side is going to be the males, the other side is going to be the females. You can see the United States, we have an example of slow population growth. Pretty even here. And then Germany would be an example of a country that has a declining population. Again, we're seeing fewer individuals under the age of 15. All right, our reproductive strategies. So, remember that we have two categories here, and I remember telling you guys, it looks like it's so clear cut. But most organisms are going to have characteristics of both. So we have our R selected and our K selected. R selected, the R here is representing a high growth rate. K selected, this is representing a population that's going to stay around the carrying capacity. So remember the capital K here represents the carrying capacity. So we said R selected, organisms are going to have a high growth rate. Again, that lowercase r stands for or represents the growth rate. And our capital K here is going to have a slower growth rate. R selected organisms are going to have a small body size versus K, a large body size. R selected, they're going to mature early so that they could produce many offspring, where the K selected, late maturity compared to the R. R selected, they're going to have a short lifespan, so their role in life is to reproduce at a very young age, have many offspring, and basically die. Where our K selected, we're going to take care of our young. So we're going to have a large body size, we're going to mature later, we're going to have a longer lifespan, we're going to have fewer offspring or small broods, we're going to take care of our offspring. Where R selected, they're going to have large broods, so they're not going to have the energy to take care of them. R selected little or no parental care, K selected high parental care. And some examples, you can see R selected, bacteria, insects are examples. Our K selected, humans, elephants. Again, many organisms share characteristics of both. So it looks like everything's so cut and dry here, but it's really not what we see in nature. All right, carrying capacity. Remember that the carrying capacity is the maximum number of individuals that an area can hold or support. And you should be able to look at the graph of carrying capacity. And here we have a number of paramecia. This could be any animal or organism. And time on our X. Notice that this is an S-curve, and that this population has reached their carrying capacity. So the carrying capacity is the maximum number of individuals that the environment can hold. And we see that growth, that exponential growth, that J-curve, eventually turning into an S. And the carrying capacity is represented by the letter K. The carrying capacity is a fixed line here. So here's the carrying capacity. Sometimes, and most times, populations are going to kind of linger around the carrying capacity. They're not going to just perfectly stay on that carrying capacity. They're going to increase, decrease, and it's going to be a negative feedback. Sometimes we see populations that overshoot their carrying capacity. If they overshoot that carrying capacity, it means it's going to pass the carrying capacity, and then many times we see a sharp decline. Oh, here we go. We have a logistic growth, a shape curve, versus the exponential growth, which is a J-shaped curve. And, oh, here we have an overshoot. Here we have our carrying capacity right here. The number of individuals, they're passing the carrying capacity. We see an overshoot and a sharp decline. And lastly, we have some survivorship curves here. We have type 1, type 2, and type 3. I don't actually think that there is a objective for this one, but I'll explain it. Remember that type 1 survivorship? This is for an organism like a human or an elephant that is going to make it through their young years, and then they're going to basically die when they're old. So there's a late loss. We have type 2 survivorship where there's a constant loss. It's typical to reach adulthood, but there's always a constant loss. So you can see lizards, rodents, birds. And then for our type 3 survivorship, we see an early loss. So here we have fish, sea turtles, and basically if they're able to get past being young or their larval stages, then they're able to survive for a long time. Also, make sure you do the couple questions the math question, and I will go over them in the beginning of the class to make sure that you have them correct. But make sure you do 1, 2, 3, and then there's one that's not numbered, and then 1 and 2 at the bottom.